Welcome, everyone, and thank you for being here today. We're thrilled to have you join us for this session exploring engine power solutions for data centers. It's a timely and important topic, and we've gathered an excellent panel of experts to share their insights and perspectives with you. Before we dive in, just a few quick reminders. All participants are currently in a listen-only mode. If you have any questions during the event, feel free to submit them at any time using the Q&A button at the bottom of your screen. We'll aim to address as many as we can throughout the session. And finally, today's webinar is being recorded. Both the recording and the slide deck will be made available soon after the event on the Engine Technology Forum's website. With that, I'm delighted to introduce our first speaker, Alan Schaefer, Executive Director of the Engine Technology Forum. Alan?
Thank you, Josie, and good afternoon, everyone. Thank you all for being with us today. Today's webinar is a production of the Engine Technology Forum, and as you can see on the right here, we are a not-for-profit educational association, and as part of our mission, that is to reach out to all stakeholders and share information and insights about key issues impacting the industry, including the one we're about to talk about today. Our members are leaders in advanced engines, fuels, and technology for both on and off-road uses, and we're delighted to have a number of them joining us today on this session. And let me introduce them right now. Our speakers today are TJ Tarabolski. TJ is the Marine and Stationary Global Regulatory Senior Technical Regulatory Compliance Engineering Specialist at Caterpillar. Mike Sanford is the Senior Sales Application Engineer with Cummins. Louise Arnold is the CAS New Business Development and Regulatory Affairs for North America. Mary Derry is the Technical Director of Performance Additives at Innospec. And Brian Ponstein is the Senior Project Manager for 60 Hertz products at Rolls-Royce Power Systems. Thank you all today for being with us. Finally, please note that the slides presented today are a collective view of ETF members and don't represent any individual member company perspectives. So data centers are a topic of frequent discussions. You see it in your daily paper, on the evening news, on social media, and the discussions cover a wide range of topics, and some of them are represented here on this introductory slide. Today's session is going to cover only a few of those topics. We won't be getting into issues covering construction, land use, or economic impacts of data centers, but rather we're going to focus on two areas. One, dealing with power supply for data centers, and the second, with environmental aspects of that activity. Our plans are to review that in this first section. Then we'll talk about the role of internal combustion engines and how they're utilized at data centers in various ways. And finally, we'll get into some policy considerations for data center generators use at data centers. And this can include things like permitting, operations, limitations on on-site testing, and a whole range of issues, many of which you may be familiar with. So with that, let's start with a little bit of a look at what's going on in the world of electrification and power. Our world is really demanding more power, and thanks to the electrification of some of our vehicles, the growing use of heat pumps for our homes, and the demands of our always on and always connected digital world, we're always looking for more power. And no doubt you've seen these reports in some of your own communities. According to the recent studies by the Pew Charitable Trust, electricity demand is expected to grow in the US by about 25% between now and 2030. That's just 5 years away. Demand in some regions is already outstripping the supply, and the ability of our aging grid system to deliver that power remains a concern. That same study annually projects that we'll need about 80 gigawatts of new capacity for each of the next 20 years to meet that growing demand. And if we just look at data centers, they are projected to be 6% of the total power demands in the entire country by just next year, 2026. That is an unprecedented situation that we're finding ourselves in. The graph on the right from S&P Global sums up this huge difference between demand and supply and the time frame for which it's occurring. As you've heard and read, data centers are a major aspect of growing electric power demand. This is from the American Clean Power Association. And you can see on this slide their work identifying the growth in power on the right and that curve. And this chart on the left shows you the differences, the change in load and energy demand by region of the electrical system operator. Many of you are familiar with how the electric supply system works in the US. We're not going to go into that now, but each of these horizontal bars on the left side represents a region of the country and the electric power supply and grid in that region. PJM, for example, manages the electricity grid and wholesale electricity market for 13 states, basically along the Northeast, but also into parts of Michigan, Indiana, and some other places as well. So that's key. And you can see from the orange dot, this is the projection of the shortfall in power. They're calling it a crunch between what the estimated growth is and what the available supply is. You can see the data center is represented in the darker teal color there, manufacturing in the lighter teal. So we have a situation where we have lots of demand for power, and we know the role that artificial intelligence has in delivering that power. And we've all seen the average for a ChatGPT query. It needs 10 times as much electricity to process as a simple Google search. And you're familiar with some of those existing ChatGPT platforms there. AI is also poised, according to some reports, to drive 160% increase in data center power demand. With all that need for power, it must remain on at all times. I think that is kind of obvious to all of us. Data centers are at the intersection of our information superhighway, from which all of our digital traffic travels. Power outages can be not only inconvenient, but quite expensive. And one estimate, it puts it at about $9,000 per minute. Outages and disruptions are occurring more frequently, according to the Energy Information Administration. You can see that graph on the right. And ensuring that data centers remain functioning seamlessly is really a key part of the use of backup power systems like advanced diesel engines and other technology. You don't want to be on a webinar like this one, for example, and have the platform that's running Zoom suddenly lose power, because then we lose all of you. And that creates a disruption for all of us. So we want to make sure that electrical power stays on, and that means on even if the grid isn't able to deliver that power. So that's a brief overview of some of the power supply issues, the very basic things. Now let's drill into the details a bit more and try and define data centers and highlight the role of internal combustion engines in those various applications. So what is a data center? This is somewhat of a loosely defined term, I would say, in the media and other places, and you can see some definitional terms here. But in today's world, if your family is anything like mine, you've got a household where you've got several tablets, a bunch of computers, a router, a modem, several connected Wi-Fi appliances. Sometimes people joke and say that I'm running a data center. That's not exactly true. It might be true in your mind, but actually a data center is a very sophisticated network and place that houses all of the traffic that moves through all of these kinds of systems and communication activities that we all depend on. And some examples of those here representing the obvious ones: Microsoft, Google, and Meta, Amazon, e-commerce through banking, Bank of America, Walmart, our educational system, the example of University of Virginia, our healthcare system, and federal governments and state and local governments as well. So we all understand how much we're using the digital world, cloud computing, et cetera, these days. There are different kinds of data centers, and I'd like to bring our panel in here and maybe offer some insight into that. And we've heard, things like enterprise co-location, AI data centers, regular data centers, hyperscale. I'd like to ask our panel of experts to give us some clarity on kind of what all these terms might mean. Who wants to start with that?
I'll jump in first, Alan, and hopefully you can hear me okay. One thing I would certainly note is the broad range of what makes up a data center. I've been in data centers that are as small as single or tens of megawatts of capacity that are built in a former, commercial retail outlet. And I've been in data centers that are hundreds of megawatts inside and have halls as far as the eyes can see. The purposes of these data centers may be entirely different, offering solutions for an enterprise operation or trying to reach their customers, their end users, wherever they may be. The differences in data centers is staggering, or can be, but they're all often, as you said, typically just called a data center. As we move forward and as this industry continues to evolve, it's going to be critical to understand the differences in each of these different types, because they do tend to act a little bit differently. And I'm confident we'll explore a little bit of that here later today.
Great, thank you for that, Mike. Anyone else want to add in on that? Okay, if not, we'll forge ahead. So let's talk about data center power. This is sort of our version of Power 101. On the left-hand side, you see a box that says prime power. And really that represents the electricity that's generated off-site by utilities and transferred by grid to the data center. And this is what powers the data center every minute of every day. And it is the way that most data centers are powered, but not all. And we will maybe mention that as we get towards the end about some of the changes that are occurring with on-site power being brought in more. But for our purposes here, we want to focus on 4 examples of on-site power, particularly those that use internal combustion engines. And these 4 areas are the following. First is the emergency standby power. This is if power goes off on site. Second is prime power, and this provides other emergency support to the grid. The third application is demand response, or what's sometimes called peaking. And then the last one is bridge power, this filling in gaps in time or power capacity. So let's explore each of these areas in a little bit more detail. Before we get to that, I thought we might like to visualize what it is we're actually going to be talking about. And you can see on this graphic a few images of generators in different configurations. And we'll talk about some or all of these different kinds of configurations as we go along here. I want to start with emergency standby grid power, and Mike Sanford from Cummins, let me just turn it over to you to give us some insights about what that means and how things are operated there.
Absolutely. Happy to weigh in here. The reality is almost every data center installed globally has some sort of an insurance policy, if you will, for the inevitable, which is a failure of the normal source of power. That insurance policy is typically made up of a number of reciprocating engine-driven generator sets, or just generators, or gensets, as you may call them. And when we say every one of them has them, it is because, as you said, Alan, downtime, not having that normal source of power, is a direct loss in revenue or operational for that individual site. And so having to quickly transfer from that convenient and economical normal source of power to on-site power is critical to ensure that those data centers minimize their downtime. As such, that drives the requirements for what those on-site reciprocating engine generator sets may look like. It's typically critical that they have a relatively fast response time. They're able to start up and offer load or provide support to the loads on site as quickly as possible. In most cases, that's under 8 seconds or so from the time that they're called to the time that they're providing power and have brought that facility back online. Most data centers will operate on an uninterruptible power supply, or UPS, for that short period of time, so they don't suffer a true outage. But a longer duration outage could be carried by a generator set. Most generator sets installed at a site or at a data center are typically installed with some level of redundancy. In addition to just kind of insurance policy with these generators on data centers operate with N+1 or a number of redundant generators to ensure that even if there is a failure of one of those, there's additional capacity to pick up the loads on site. Typically, most years, the generators on a data center site will operate fewer than 20 or even fewer than 10 hours annually. It's not a typically long period of time, as most data centers aren't being built where there is current grid instability. It's not convenient or economical if that's the case. And so the generator set is truly there to operate in the rare chance that that normal source of power has failed. In many cases, these generator sets and engines that are contained within them are susceptible to some sort of permitting requirements or air permitting requirements, both at a federal level through the EPA, where the engine manufacturer is responsible for the qualification and certification of the engine, as well as a locally derived or mandated permit, typically at the state or process. In many cases, to satisfy those emissions requirements, it's not uncommon to see additional technologies deployed alongside that engine generator to reduce the emissions output from that genset to lower levels as determined by that local permitting authority or air board.
Okay, Michael, just a question for you. So, talk to us a little bit about what happens in that moment that there's a problem with the grid and the power coming into the facility cuts
Yeah,
off, and sort of how does that whole process manage? Is there somebody going downstairs with a plug and unplugging one thing and plugging in another?
No, certainly not. So generally in most data centers today, they're a modular design that actually splits the loads within the data center to isolated halls where individual pairs of generators will data center. The systems, the switch gear that intercepts that feeds the normal source of power to the loads actively monitors the condition of the utility, normal source of power being utility. And when it detects that the normal source of power is no longer adequate for the site, so the voltage or frequency has deteriorated sufficiently so that the loads can no longer operate as they normally would, it initiates a transfer. And that transfer could be a result of a total failure of the normal source of power, a power outage, or it could simply be a brownout condition where the voltage or frequency have decayed to a point where they're technically still there, but they're probably not serving the loads appropriately. In that case, that transfer begins to take place. The sophisticated controls on site call the generators to turn on, to begin spinning up. And once they're available and able to provide load to the site, the mechanisms in the gear itself physically move the connections themselves through a series of circuit breakers, typically from the normal source of power and the path that went from the normal source of power to the loads to the emergency circuit, which is typically the generator sets on site. And this, again, happens very rapidly and typically a period of fewer than 10 seconds overall from the time that the normal source of power has failed to the time the generator sets are online. Alan, did that answer the question okay?
Yes, got it just right. Brian, TJ, you guys want to weigh in at all on that?
The only thing to add to that is it has to be highly automated due to the times that we're talking about. We're not having people sit there 24/7 just ready to move wires from A to B. We physically would not be fast enough as humans, which is why this is all highly automated.
Okay, very good. Let's move on to our second area of power that internal combustion engines are involved with data centers, and that is demand response. And this is bit of an explanatory slide about that. Let me turn to Brian Bonstein from Rolls-Royce Power Solutions for his take on demand response and what that means.
Thank you. Demand response is something that shouldn't really be too new to anybody. This is to where what we have is we have a grid that's available, but we don't have necessarily enough power to power up everything. And this is to where you may have heard of brownouts or blackouts, to where parts of the electric grid get turned off to help preserve the overall. So that's a case to where we see that today. Now, how we often look at this and how maybe you at home are dealing with this is you may enter into this as your own user, to where your air conditioner under peak power, your utility provider has the ability to not allow your air conditioner to turn on, or your water heaters. And then they typically do that for certain periods of the day to where these peaks would be the highest. And typically for your AC, this would be, I call it afternoon timeframes, to where you're coming home, you've told your air conditioner to turn on to cool down your house, you're still at work, and we have both of these two situations going on that we start to stress the grid. And this is to where demand response would take over and we might remove some of those loads. The other way that we can deal with this is by adding resources to the network. So this is by activating these standby generators that Mike was kindly talking about. And these backup generators would then turn on and could run during this period. However, it's not just as simple as turning that on. We need to make sure that these units are meeting the applicable requirements specified by the federal government. So to run in a demand response case, you have to meet the non-emergency regulation, which is typically going to be a tier 4 type application for a diesel unit. Gas applications or bigger units, that could be a different case, but generally that's what we're looking at. So one of the key questions that we have to ask is, what do I have today? How does that unit need to run, and what equipment do I need on there, or what certification? So this is to where it's very easy to have this asset and a switch of a button turn into these applications. But if it's not built correctly to where it has the proper certifications to meet that, it might not be the case that we can actually do that. So in many cases, we have these assets sitting there, but we can't run them in demand response today. That may change in the future, and hopefully it does, to where we can find solutions for that, because there's a lot of these backup units in the market today, and they're only needed for, I forgot what slide that was previously, Alan, that you showed. I want to say it was like 10 or 12 that showed that we only need a few hours a year. It's not very much to actually combat this and deal with it. We would have that available, and we would need typically it's an after treatment system that goes on these. So it would be an SCR and or DPF system that would be needed to meet those requirements. And that period that's needed, a lot of these programs, you sign up for a 500-hour requirement. Some of them are drastically less, some of them are right around that 500 hours. But in reality, that 500 hours is not needed. And it's just a couple of hours each day that might be needed for this demand response to help curtail that aspect. And then, yeah, the emissions control, just to touch on that again, we are looking at some type of after treatment system to meet this, and this is to meet the federal requirements, and then often there is local requirements that may also need to be followed or met as well, that could go above and beyond the federal requirements, but generally not.
So one question, Brian, is every data center that has an emergency standby generator able to be part of a demand response kind of a program with the local utility, or is that only of certain types?
That's a key question to understand. I like how you phrased it. Could it be? Because could it be? The answer is yes. Are they capable to do that today? The answer is no, and that's because they don't have the certification to run in a demand response application. Policy could be changed or adapted to allow them to meet that. So a lot of these large clients are putting on after treatment systems just due to local requirements that are very, very similar, if not identical, to a Tier 4 certified unit, as long as I stay on the diesel side. That is basically the same. So, but it's not certified, and there could be a way to leverage that and make that happen in the future to where we could deploy these assets and drastically shrink that gap that we currently saw in those previous slides. So in essence, yes, they could be, but can they be today? There's legislation that needs to be adjusted to allow for that. And it would allow for a very reliable grid for us to have.
Great, thank you for that. Okay, any others want to weigh in on the demand response part of this?
I would just note
Okay.
that this was, sorry, Alan, I would just
No.
note that this was recently addressed, actually a few weeks ago, by the Department of Energy Secretary Chris Wright, addressing the opportunity to leverage assets like emergency generator sets in order to help in periods of demand response in order to potentially reduce or eliminate grid instability. A great interview that I believe was conducted just about a week and a half ago.
Excellent point. Thank you for sharing that. Okay, let's move on to our next type of power, and I'll take the lead on this one. One of the things that you've heard about, and we've seen reported in various news reports, is the rapid growth in the data center community. And assuming that the land use and zoning issues are resolvable, the construction of data centers can occur in quite a rapid kind of clip that you have within 8 to 12 to 16 months, you have a fully operational data center that's set up, outfitted, and ready to go. And in some parts of the country, the electric power grid and the local utility are not able to provide power to that new data center in that same time frame. They may be a few weeks difference, they may be a few months different, or it could be longer. But in any case, the data center landowner, data center tenants then are faced with a situation where they're ready, but the grid is not quite there yet. The utility cannot guarantee them the power they need or the time to provide the power in a time frame that they need it. So that is a situation where there is a need to decide what to do. And one of the things to do is what is known as, I think informally, mostly as bridge power. And it's somewhat the same kind of application as Brian just discussed. And that is that we have these standby generators on site that are deployed to be used in the emergency standby mode when the data center is up and fully running. And we're waiting for that point to happen. So we have these power assets sitting there. Is there a way to leverage that so that the data center can come online and be more available in a shorter time frame? And so the idea of bridge power is, of course, that we're bridging either time or capacity. And the capacity issue is one where the utility can provide a certain amount of megawatts, but can't guarantee the maximum amount that the data center would like to have. So maybe they can start up part of it, but not all of it without the utility being fully ready. So in this instance, this bridge power operation can take place where those assets that are already sitting there can power that data center for that duration of time in a fully permitted way until the utility is able to provide the level of power and to connect the power for the actual data center to then rely fully on the grid for its prime power. So this is an area that is emerging in some parts of the country as more and more data center investment goes out. We're seeing the utilities not able to necessarily keep up with sort of a simple supply and demand system that we have today. We have more demand for power from the AI related data centers, and they're going up rapidly, but not able to deliver that in a time frame needed. So just to kind of talk about this a little bit more, let me just open it up for comments from our panel of experts here. I think, you know, this is in many ways like the demand response, if I'm not mistaken, and that means that we've got to have a certain level of permitting and emissions control to be able to even go down this road. Is that right?
Yeah, these are subject to the same permitting requirements, if not more stringent, because of the amount of hours that are going into these units.
Okay. And what about fuel types for something like this? Is if we're going to be running power for a longer amount of time, is there anything there relative to the fuel selection, fuel technology choice?
We've seen cases to where gas becomes the common choice when we look at it here, because this becomes the OpEx side of things, because running on diesel fuel becomes pretty expensive in comparison to the natural gas. That just seems to be the case as soon as you get over, I call it that 500-hour mark, maybe even a little before then, that your economics start to play out, that it makes sense to switch over to a gaseous or lean burn type application.
And Alan, practically at the moment, there are so many data centers being built. It can depend on the location. So if you are close to a gas line, a gas pipe, then maybe gas is your best option. If you're not, then you might be looking at diesel, assuming that you can get the right size of gen sets, because again, a lot of manufacturers are really seeing a huge increase in demand. So can you get enough both for backup power and prime power to source your power needs? So it's a really complex question at the moment, and everybody's being creative in their solutions. And in terms of emissions from continuous operations, that is almost 100% likely to put you into that tier 4 requirement with SCR. And if you're going to have almost continuous operation, then yes, you're into air permits and very strict controls and reporting. But I'm quite happy to tell you that the after treatment systems that we're together putting on these engines will make sure that your emissions at the tailpipe are going to be very, very clean. So from a neighbor perspective, we can make sure that we're not emitting pollution, and we can make sure that we're doing something about the noise generation. They're never going to look particularly pretty unless you love industrial art. But in terms of the other problems, then we can do a lot. And if you're using renewable fuels, you can even start to see the carbon footprint coming down quite significantly as well.
Some great points there. We're going to delve into a few of those more deeply here in just a moment. But thank you for that. Very, very important part of the discussion right now relative to data centers and their growth. Okay, so we've kind of laid out the different power options that are using internal combustion engines at different types of data centers. Let's get into a little bit more of the details on fueling and emissions control. That's a great segue that we just had there. Thank you, Louise. So you've heard Brian and Mike talk about demand response, emergency standby. You've heard the frame of references tier 4 generator. What does all that mean? And for that, we're going to turn to TJ Tarabalski from Caterpillar to walk us through and help us understand what these different pieces of nomenclature mean and what that means in emissions and how long things can be used. So TJ, thank you in advance, and the floor is yours.
Thank you, Alan, and good afternoon, everyone. Thank you for joining the call, and thanks again, Alan and Josie at ETF for the work you do there. Appreciate you arranging this webinar. In the beginning, when Alan and others were talking about the emergency power, it reminded me I was at a data center on 9/11, and the thought just occurred to me how different that day would have been if the grid was down. Imagine that for those who lived that day. So this slide highlights for us the operating restrictions for tier 2 and tier 4 engines in emergency and non-emergency applications. It doesn't cover all the potential operating scenarios and permit requirements that may be applicable to installations. So owners and operators should consult with their approved legal counsel to make final compliance decisions but we're trying to make the complex simple here for all in attendance. And the market feedback in this case is from end users, regulators, engine and aftertreatment manufacturers. And as a backstory, EPA included emergency, I say quote, emergency use only engines as a unique case in their 2006 stationary compression ignition engine rule. Emergency use only engines may be sold in the US with owner operator restrictions since Tier 4 went into effect in 2011. And this was central to allowing Tier 2 engines still to be placed on the market when Tier 4 is otherwise required. By rule, Tier 2 engines can only be used when the normal source of power is unavailable, which Brian highlighted earlier. In the US, emergency use only engines typically operate less than 50. Mike had said 10 is the number they see often. Not uncommon to be at very low hours per year, but they often provide critical life-saving power directly in those very few hours for hospitals, nursing homes, or indirectly by keeping communication infrastructure operating by powering cell towers, data centers, etc., when grid power is unavailable. And end users have provided the feedback to manufacturers on how regulations and operating restrictions could be adjusted to provide flexibility while not compromising environmental protection for installed and new engine applications. These moves would help facilitate EPA's effort to support AI with installed and newly installed data center power systems. The first column on this chart lists the purpose of an engine's operation. In the first row, I'm calling out emergency operation. The second column lists the US EPA certified tier. Here, Tier 2 engines are emergency use only. We jumped ahead, Alan. Are emergency use only, and Tier 4 engines are for non-emergency operations, recalling they can be used for emergency purposes and have a dual purpose role. And you can see that both of these engine types, the Tier 2 with after treatment or without it, can be used for emergency purposes. And a Tier 4 engine can be used for emergency purposes. So this Tier 4 engine may perform both emergency and non-emergency functions. The third column lists the hours of operation by engine type and the operation allowed by the current US EPA regulation. Gray indicates a regulatory change that, if implemented, would improve adoption of certified Tier 4 engines by removing inducement, which I will describe in a moment. Green, as I mentioned, indicates allowed annual engine hours, and red, which we haven't seen yet, but we're going to see a lot of it in the next categories, indicates prohibited operation. Inducement is a required feature of Tier 4 certified products intended to induce operators to perform maintenance by forcing an engine to shut down automatically if there's an emissions-related malfunction. However, stationary engines have state air permit reporting requirements that typically require notification of malfunctions to the state permitting authority in a matter of hours. Subsequent state requirements to shut down engine operation, potential fines, or both make the automatic engine shutdown a redundant instrument to induce proper maintenance. So now that I've explained the first row, the green and the gray, now that you understand those key terms on the slide, let's go back to the first column and start with a reminder that a Tier 2 engine is for emergency use only, and a Tier 4 engine is for non-emergency operation, but that those Tier 4 engines can serve dual purpose. Next slide. In row 2, this is the other emergency category, which is in the regulations today. And it allows emergency engines to operate up to 50 hours, but this is a narrow application providing power to an isolated grid, for example. Tier 4 certified engines can operate without restriction on hours. In either case, additional state permit restrictions may apply. If I just jump back to the first row, that testing and maintenance that I mentioned, that is considered non-emergency operation, much the way that this first 50 hours here for the Tier 2 engines with or without after treatment are allowed to operate. Next slide. There we go. Thank you, Alan. The third row describes peaking and demand response restrictions on hours of operation. Historically, the EPA rule allowed up to 100 hours of operation for peaking and demand response, but this allowance was vacated by court decision in 2016. Consequently, when you look at this Tier 2 engine with or without after treatment, it is not allowed to operate at all for those purposes under the current regulations. Tier 4 certified engines can run unlimited hours for these purposes as shown in the green. So this covers peaking and demand response as mentioned earlier by Brian, and the emergency operation also as discussed earlier. Next slide. The fourth row is the baseload prime power or bridge to grid as Alan was describing. This describes the Tier 4 certified product may be used for this purpose, and potential changes to the EPA regulations could allow the Tier 2 engines with advanced controls to run additional hours. They'd be meeting the same emissions levels as the Tier 4 product in that case, but it relaxes the restriction of limiting their operation to emergency hours only by adding the after treatment. And as noted earlier, for all these scenarios, additional state restrictions can apply. So going back to the idea of making the complex simple and jumping to the next slide, Alan. Removing the inducement here shown by the X's for the certified Tier 4 engines places the decision-making process in the hands of an end user subject to state and local compliance requirements for all the scenarios shown. As mentioned earlier, reporting to state authorities is in effect today if an emissions-related fault occurs. These faults or alarms are an infrequent occurrence, as you might observe in your own vehicle. But unlike mobile equipment, stationary sources report malfunctions to permitting authorities, making inducement redundant. In summary, adjustments to regulations can provide greater operational flexibility by allowing Tier 4 engines without inducements and emergency use only engines with after treatment for use in peaking, demand response, and prime operations as mentioned above. If these rule changes are considered and implemented, they will place critical decisions within the control of the operators and end users. So thanks again for the opportunity to explain the complex here, and hopefully it helped your understanding. And back to you, Alan.
Thank you, TJ. This is really a critical part of this very complex area and how generators are used and how they must meet certain emissions criteria. So this was, I think, an excellent presentation, and for everyone trying to understand the different types and how they're used, this is going to be quite helpful. Let's turn now to some bigger considerations on fuel and emissions. And for this, we have a bit about fuel quality that we'll get to in just a moment. But I would like to get us into a discussion about what we see in terms of in the field for different fuels and technologies and what goes into that. This is a key part of the data center operator, the tenant, if you will, whoever is the firm that's operating that particular data center has to make a decision in the design phase about what kind of fuel they'll propose to use for their facility. I say propose because all of these go through a permitting process, and there's an opportunity for discussion about that. We know that you've heard already today all three of these fuels mentioned: diesel, particularly in the emergency standby setting, natural gas, and then as well as renewable fuels, renewable diesel or HVO, which we'll hear about in just a moment. We know that because these generators are so critical to the operation of data centers, being able to start up reliably is key. And so having a very high focus on fuel quality is important here. And so for that, let me turn to Mary Derry with Innospec for a discussion about fuel quality and what that means for data centers. Mary?
Great, thanks, Alan. If you can go to the next slide, please. As you all can imagine, many of these data centers have numerous generators contained within them. And to power those up, even just for their monthly or weekly tests, they will have lots of fuel stored on site. They can have anywhere from 10,000 gallons to 1 million gallons of diesel fuel on site. And while diesel is a relatively safe fuel to have around, it's not as volatile as gasoline. It does have issues, especially if you store it for several months or over a year, if that doesn't get consumed in the regular generator cycles. Next slide, please. The terrible thing that can happen, and we all know about that in your car in the winter, it'll pick up water in your gasoline engine, but diesel will also pick up water. So if it sits in a tank, and of course there's some kind of headspace there, it gets cold, it gets hot, water will accumulate in the fuel. And once water accumulates in the fuel, you'll have this interface of organic and water. And at that surface, what likes to grow there? Bugs. So you have these cells growing, these icky biological cells, and it becomes very gicky and gunky, very scientific terms. You can see that fuel filter on the right where they're scraping off the scum off the filter. And this is a problem. It's bad for your fuel. It won't run. And another problem you'll get is if it sits in the winter and the power goes out and that fuel has not been treated with the appropriate cold flow improver. In the winter, all diesel is treated with cold flow improver because it will gel up. And if you don't have that, you try to run in the winter, you'll have a solid fuel. So to keep your fuel integrity proper for the long term, one should always use some form of detergent and cold flow improver to keep the water either miscible and flowing. But then if the water gets too high, you're going to need a biocide to prevent that scum buildup in your diesel fuel. And what will happen is you'll have to do major tank maintenance where you drain the bottom, you drain the top separately, and then go inside and clean it. And it's not easy. So the easier solution is to just use the proper fuel additives. Next slide. I'm done. Thank you.
Thank you, Mary. That's an important highlight for not just for generators, but for all of us using fuel in our vehicles, et cetera. I do want to turn to the discussion about renewable fuels and bring in our panel here and to talk about sort of what goes into data center tenants. How do they select the different fuels? Are they always picking diesel? Or are they sometimes picking natural gas? What goes into that? One of the things that we have seen over the last few years here is a growing interest in the use of hydrotreated vegetable oil, or HVO, also sometimes known as renewable diesel. And you see a little news clip here about Amazon Web Services and some of their interest in this product. And we know that manufacturers are also quite interested in helping provide sustainable options for their customers. So I'd like to open up to the panel here for some discussions about what renewable fuel choices we have here and what you're seeing out there in the field. What are your customers getting when they talk about HVO and renewable diesel? What are you hearing there?
Well, I'd like to make a comment on that, if I may, please.
Sure, absolutely.
So with diesel, as Alan mentioned, there's this renewable diesel or hydrogenated vegetable fats, vegetable oils, and it's a great alternative. And some manufacturers are selling it as a drop-in fuel for diesel, which it is because it's basically the same weight, viscosity, etc. However, it has special properties depending on how they make it. It goes through a process called isomerization, which branches it so it doesn't get solid at cold temperatures. But some quality of HVO is not as good as others. And also when you mix a low quality HVO with a high quality HVO, it can ruin the integrity of the good HVO. So while HVO comes from a renewable source, it still makes deposits, it still picks up water, and can have an even tougher time at cold temperatures and staying liquid. So you still have to consider your fuel for your long-term storage. Additionally, HVO is in limited supply. It's not like diesel fuel where we get it out of the ground, we refine it. There's, you know, how many hundreds of thousands of barrels a day. HVO is in smaller facilities and it's being used exclusively right now in California, parts of New York, and some other states. And there's really not a lot of it to go around. So it tends to be a bit higher priced as well. And now I'm done.
I love that, Mary. You put the importance of, I oversimplify all of what you said into know your fuel. If you don't know what's in your fuel tank, if you don't know what's in there, that's going to cause you more problems. It's no different than just relating it to the human experience. If you get sick, you don't just automatically pop a pill that you grab out of your cabinet. You know what you're dealing with and you grab the proper pill for that. So know what you're putting in your fuel tank. There's lots of advantages to HVO. There's lots of advantages to every fuel that's out there in reality, but know what's in there and know what it's doing for you to meet, in this case, typically with HVO, we're trying to address a emissions topic that I can address today with a standard unit. And it's a great solution, but however, be aware of what's in your fuel tank and know what's in your fuel tank and take care of it properly.
From a emissions control system, it's almost exactly the same. What we do see is, in terms of how cleanly it burns, we can sometimes see some impurities collecting on the catalysts, so that can cause them to have a different aging profile. But broadly speaking, it's, from an emission standpoint, a drop-in as well.
Okay, others want to weigh in? Yes, go ahead.
I was just going to tie in a little bit of what was just stated as well. Like, feel free to reach out to us as manufacturers. We will help you with this process. If you need to know, does this fuel work or not? Ask us those questions. We can look at that whole system of what we've supplied you and what works and what doesn't work. We're your experts there.
Indeed. Okay, let's move on then to our next topic, which is one we've dabbled about a little bit here, and that's the environmental profile from an air and a sound perspective. And I want to start with the sound part of this, and then we'll get to a deeper discussion on emissions in just a moment. But a lot of times what we see in terms of our work dealing with various groups and others with data centers and concerns about noise, the principal source of noise at the property line is often due to the actual data center itself, and that means principally the heating, ventilation, air conditioning system. How are they providing cooling for the data center inside? The servers create heat, and that heat has to be dealt with in some way, either through cooling fans and using water or some other different strategies. But by and large, that and just the electrical hum from a large concentrated area of computers is the principal source of noise for data centers. As you've heard repeatedly today, the standby generators really are only running a few hours a year. So if we're talking 10 or 20 hours a year, you can imagine how that's sprinkled out over time. So it does not have a very significant impact on the day-to-day kind of noise concerns that are had. And as you see on this slide here, data center tenants can specify very sophisticated noise attenuation units. And you see a diagram of one in the upper right-hand corner. And Brian, I'll let you speak to what that is, just because it's your product and you can explain it maybe better about the noise aspects of it and how it exists there.
There I go with a common problem. I was doing this proper sound attenuation. So what we have is we have a big radiator fan that's pushing across there, and there's different solutions for this. There's remote cooled and there's unit mounted radiators. Typically in North America, most of your units are sitting with a unit mounted radiator, so it's very similar to where your car drives it right off from the engine. However, there's not the clutches that exist in your car. These are usually direct drive, so it's constantly spinning when the engine is spinning. And that's going to create some noise, but all of these units are built to some noise level requirement. Often what gets specified is a 75 dB requirement. Sometimes that's 85, even 95 is often a requirement. Getting much lower than that is less common. But how quiet is that for those that don't understand? What you're probably listening to right now is probably already the upper 60s from a dB perspective. So that's a typical conversation. So it's really not that loud when you think about it, and that noise is going to, over distance, going to get quieter. So as we get further away from the source, it's going to become quieter and quieter. So it doesn't actually become that loud. What we do see as we get into remote radiators, we can have different fan setups, and we can actually get that to a quieter level as well. But these are going to be in extreme situations and generally have significant cost impacts as well. So every dB reduction that we're reducing does have big impacts for the cost of the unit for what that means. And there's often other solutions as well, to where we can blow the air upwards, or we can put walls up, things of that sort. And all of these cases are used to help mitigate the sound penetration leaving a facility.
Great, thank you for those insights. And my last comment on this slide is just the chart on the left, which is ours. It does give you an idea of what's happened over time to diesel engine emissions generally. This includes highway vehicles as well as off-road engines and equipment, of which power generators are a part of. And you can see since around the 2014 timeframe there that these emissions for both nitrogen oxide on the right and particulate matter on the left for new units manufactured in those years and later are truly near zero. That doesn't happen by magic. It happens through a very sophisticated set of technology. And here to help us understand what that is in a moment is Louise. You've heard from her already. I did want to, though, bring up this slide from Virginia, because it is one that is instructive to us. And the Northern Virginia area is one of the highest concentrations of data centers in the country. And because of that, they're a little bit out in front of understanding a lot of these issues compared to others that are just starting to see data centers be brought up for discussion. And they evaluated their community of data centers there from a wide variety of sources. And the Joint Commission on Legislative Auditing in Virginia published a fairly lengthy report of which it looked at emissions as part of that. And you can see some of the findings here, their conclusions. I won't read over theirs, but in this instance, you see they said that backup generators were less than 4% of the regional nitrogen oxide emissions and less than 0.1% of carbon monoxide and particulate matter. And despite the permitted values might being quite high, the emissions were really only 7% of what permits allowed. So even though a lot of data centers have been added to the area, regional air quality has improved. So just putting the data centers in place there, and this finding, I think, demonstrates the great technology that's available to virtually eliminate emissions of NOx and PM from these units. And so let's maybe learn a little bit more about that. And Louise, can you give us some insights, please?
Certainly, Alan. So we are seeing a range of sizes and power for the engines. We've discussed a little bit tier 2 versus tier 4 emission solutions. So that tier 2 will have a particulate filter, an oxidation catalyst included as a minimum. We can see these on a power range from a very small custom engine, maybe about a kilowatt, through to the 10 megawatts or larger large engine systems. So the scale of the solutions changes with the size of the engine. So when we're starting to look at tier 4 solutions, that's when we're adding in an SCR catalyst solution, and this will help to manage the NOx emissions from the engine. And on sites which are very large, depending on how they're permitted, we can actually see a mixture of tier 2 and tier 4 engines on the same site. So we can provide a range. Also, it is possible to make these solutions modular. So maybe you start with a tier 2 new engine, and then you change or expand the use, or there's a change to the permit, and then you can add a SCR module at the end to bring those emissions down, or if there's a local requirement to do more than how you've started with the engine solution. So there really are all sorts of things that we can do here, and depending again on the location, the proximity to the neighbors, these solutions can have additional acoustic packaging, additional silencing to make sure that they meet the other requirements on top of those emissions solutions. So if you go to the next slide, Alan, and this is fairly complicated. It's not going to be a quiz on this later, but it really just shows you how we build up that SCRT system. So that's, you have the engine, it's got the oxidation catalyst that comes out, we measure the performance, we dose urea into the system, which is the DEF, which we then make sure that the SCR catalyst has enough of that reduction agent to be able to convert all of the NOx that's being exposed into the system from the engine emissions. So there's all sorts of ways of treating the after treatment and packaging it for the space and the size that we have available. If you've got a very big engine, you're going to have a very big after treatment system. That's just how these things scale. So very often they'll be mounted on top of the apparatus, and if you've got maybe the genset could be mounted even on the roof of the facility. So that's where we would locate the emission system. It's going to be right next to that engine. So there's very little additional real estate normally required. Again, it depends on the individual makeup of the and design of the engine and how that's located on site. Next slide. So yeah, here we have some of the installations that you've seen. So if you like industrial art, the grey boxes in the top right, you can see there's a little slightly smaller box on top. All of the emissions control is contained within that anonymous grey box. Again, the center picture, that the black boxes, there's a slightly smaller black box. I think these things look like tanks. So the little command unit on top, that's where your after treatment system is. So you won't be able to say, aha, that's the after treatment system. It's all packaged very neatly and very anonymously within the genset itself. So yeah, that's the after treatment system. Big grey box.
Excellent. Thank you for that explanation. I guess just a couple of things. One is, what about, let's say, an older generator that's maybe a tier 2? Can they be retrofitted with SCR systems?
Absolutely, they can. You can put a standalone SCR system on the back with NOx monitoring. Mike, are you talking as well? You're on mute.
Just agreeing with you, that's all.
Yes, so it's very possible to retrofit diesel engines from a tier 2 to a tier 4, or even if you've got a pre-tier 2, you can still upgrade your emissions. Tend to see it more in the marine industry because big boats work for a very long time, and the emissions are constantly changing for those. But a diesel generator does not know whether it's on land or sea.
Okay. Others want to weigh in on that?
The only thing to add is that this is not something new for somebody that might think that adding after treatment is something new. We've been doing this. I don't know, Louise, if you want to comment how long you guys have been doing this, but it's many years. It's the easy way to put it. People might remember Rice and ESHAP. That was a regulation to where we had to upgrade a bunch of units. This is no different. So this is not anything earth-shattering, brand new. This technology is well vetted and well used.
Yep.
Okay. Very good. Let's move on then to a little bit of a discussion. You've heard now about the role of internal combustion engines, different aspects of the data center website. Let's talk a little bit about what some of the other power options are. And we've got kind of a list of them here. Whoops, excuse me. And I think this is a circumstance where our members, manufacturers, provide a range of options for their customers, and there are competitors out there in the field, no question about it. But I think as what goes into evaluating these alternatives compared to what we've just been talking about today, the diesel and natural gas reciprocating engines. These are some of the areas there, and I just ask our panelists to kind of weigh in here. How do we stack up against some of these other kinds of technologies?
So it's buyer's choice. And I think the internal combustion engine has a lot of experience. People are very familiar with how to operate it. There's some very reputable companies in the industry. So it's the banker. It's the one that people know and understand. I think as other technologies come up, absolutely, they're going to be needed. We've got an awful lot of power to find. I think, I can speak to fuel cells because, again, that's some of the technology Johnson Matthey supports. Absolutely, fuel cells should be part of the solution. Very efficient way of generating power. But again, they're a little bit more unknown. They were up on the moon for the moon landing, but they haven't really taken off, no pun intended, since. But that is definitely one of the solutions of the future that we think will start to become more widely used and accepted. And I think that's the same with many of these other technologies. They just need to be adapted. They need to be seen to be used. They need to seem to be successful, and then we'll see additional adoption even.
When we take a look at the portfolio of on-site power solutions that are available today and will be available tomorrow, it is important that we really understand the use case, the application, how it's intended to be applied. It's easy to point to technologies like nuclear, for example, and say, well, this is a clean solution. It's a stable solution, maybe the right thing. It's easy to talk about fuel cells or battery energy storage and point out the specific advantages and opportunities that they offer for the data center space. One thing that I often remind others of when we're talking about primarily backup power and even bridge power applications is that pound for pound, kilowatt per kilowatt, dollar per dollar, and even pound of emissions or ton of emissions, there is nothing that competes like a reciprocating internal combustion engine today. And that may change. Certainly, it's an industry that has been developing over the last 100 plus years, and it will continue to develop and continue to be a core part of our energy infrastructure for years to come. But right now, from a commercial standpoint and a dispatchability standpoint, there's one solution that continues to lead in this space, and that primarily is reciprocating internal combustion engine driven generator sets. I'm excited to see what the next few years will hold in store for us in this space. I'm looking forward to fuel cell, battery energy storage, and other technologies and how they complement the solutions that have been developed for so many years.
Well said by all. Thank you. Let's turn now to just a reminder for participants. We have plenty of time for Q&A here coming up in a few minutes. Please submit some of that you've done already to the chat. Thank you for that. There's actually, excuse me, the Q&A box, I guess it is, that you're submitting questions to, and we'll do our best to get to those in a moment. The last thing we'd like to talk about today is some of the policy considerations that we know all stakeholders in this area have confronted over the last number of years as we've looked at these issues. And let's start by saying, as you've heard from our panelists today, there are a myriad of requirements for generators, backup internal combustion engines used at these settings. Federal, state, and local policies, a whole range of those. You've heard about how EPA establishes the emission standards and how the systems can be used, and that's a manufacturer standard. And then we've also heard about some of the new policies that have just come into focus more recently from the Trump administration that is looking to streamline and fast track some of the permitting for data centers to achieve our leadership in artificial intelligence here in the US. And so as I think as TJ pointed out, we're not quite sure exactly how those things play out, but they are in discussion at some level. And so that is a kind of a new factor, but one that's a little bit unknown at this time. In addition, we do have a myriad also of state and local requirements. Public utility commissions can be involved if the data centers are connected to the grid and putting power into the grid as a power supplier, just as a utility generating station, for example. They have authorities there that govern how the power can be connected, how much is given, what the rates on that are, and a whole range of other considerations. State agencies are typically the principal permitting ones regarding the Clean Air Act and air permit emissions. And these are also incorporated into the state implementation plans. So as a stationary source, a data center would have a permit that would be issued by the state environmental agency and be subject to all the requirements within that, oversight, testing, enforcement, whatever it might be. And then finally, local and county. And this is where things get quite local in terms of zoning issues, involvement of the community, local site conditions, and a whole range of things. And then beyond that, and we didn't talk about a lot of these today, but there's also a ton of other codes and standards that manufacturers comply with for the safe operation of generators, the safe storage of fuel, the quality of their product and its reliability, et cetera. And these are things like NFPA, the Fire Protection Code, and a whole myriad of electrical codes, as you might expect in this area. So there is quite a bit of policy, let's say, already in this space. We've taken a look at what is out there so far year to date, 2025, and there's about 350 bills that have been introduced in various states looking at some aspect of data center legislation. These run the range of things dealing with the economic and taxation implications of data centers, impact studies commission to determine what the impacts would be on the community, looking air emissions, noise, water controls, zoning and land use, etc. So quite a highly legislating activity so far this year that we've seen across the different state level. And lastly, on this particular policy point, We at the Engine Technology Forum have worked to be involved to provide resources for state and local policymakers as well as other stakeholders looking to be involved in this area and trying to understand what some of the topics are and the kind of information like you've just heard about here earlier this afternoon from our experts. And they cover a wide range of issues. And we at the Engine Technology Forum also have the somewhat unique situation in that we are located in a part of Maryland where there has just been a very large 2,200 acre data center campus emerge in the last few years. And that is one that's currently under construction. So we have had some firsthand experience about this range of topics that we've talked about today, and particularly some of the policy areas. And for TJ and Mike and Brian, this is as representatives of engine manufacturers in areas they deal with on a regular day-to-day basis. I think as we approach this, we always looking to provide best information that we have available to whoever would like to have it. And whether that's data about generators or studies or specifications, what have you, we can point you in the right direction. I will share a little bit to kick this part off with a little bit about our experience here working at the local level. And I would say that sometimes there's a tendency, policymakers might want to get involved in these areas very rapidly and start to look at and get into things that are quite complex and technical, as you've heard about today. And sometimes those can have unintended consequences. And I'll just give you one example from our local experience here. And there was an initial proposal that generator testing, which would take place on a periodic basis at a site which is going to have multiple generators, somewhere probably in the range of about 100 or so, that those generators, the county proposal was that they could only be tested one at a time. And so we tried to make a point that testing one generator at a time with a data center that could ultimately have well over 100 generators, that would result in a longer impacts to the community in terms of noise and really just make things less efficient for the data center operator and their consultants, whoever might be doing the testing, but let alone it would be more inconvenient for the local community. And so while that we understood the motivation behind that, it did create a situation where folks say, okay, maybe that's not the best idea. So if we could, let's go full tilt and let's get as many tested in a reasonable amount of time possible to minimize the impacts, ultimately works out to be a better solution. But that's just one example of sort of the issues that come up in these areas, and we welcome those in the chat room, in the Q&A box, I should say, as well. But let me ask our participants here, based on your experience in the field, what are you seeing out there in terms of policy considerations, and what can we learn from that?
I think one of the things that I'll jump to that we often see as a regulatory issue at a city, state, or other local level is particularly related to noise. Noise is one that comes up fairly regularly for truthfully any site. However, data center sites are often heavily impacted by noise regulations. For those who aren't aware, most data center sites today install the generator sets in outdoor enclosures. They're, as you saw in the pictures earlier, they're large sheet metal boxes that enclose the generator and are typically located in relative close proximity to the property line. Many of those generators, as discussed earlier, include exhaust after treatment systems, or at the very least include exhaust mufflers or silencers in order to mitigate the effects of the sound produced by the engine. I think Brian mentioned the immense amount of sound caused by just the radiator fan, and certainly that's the case, which is why you see those huge louvers on the end of those enclosures, but certainly the engine itself is producing some level of noise. Oftentimes, the regulatory issues that we see around that, as Alan alluded to, may not really address the best way to kind of protect or safeguard the community from that. So regulations that one of my favorites is seeing some that specify things like 45 decibels at the property line. Wherever you are right now, I can pretty much guarantee you it's significantly louder than 45 decibels. And that's not to say that it can't be accommodated. However, it's very challenging to demonstrate that on site when when the generator sets themselves next to a highway or some other noise polluter. Additionally, a requirement like that often significantly drives up not just the cost, but also the footprint of the enclosure. And it takes it from a solution that may not have been an eyesore previously to something that has to be monstrous in size in order to satisfy that requirement. And again, a requirement that is probably not best fit to really protect the community. There's more, there's better ways to approach it. And so being aware of that is important, and understanding how that testing is actually going to be done is critical.
Thank you, Mike. Others want to weigh in there on their experience? One more anecdote that I'll share regarding our local experience here is that we started off with a county proposed ordinance that would govern fuel storage for above ground tanks, and it seemed to have been modeled around what you would find in sort of a general local fire protection safety kind of thing, which limited it to 1,200 gallons above site with some various containment requirements, etc. And that immediately created concerns in terms of the data center's ability to meet their objectives in terms of being able to sustain power for an extended period of time before needing fuel replenishment. And so I think the initial volume storage allowed was like 1,500 gallons. And that was probably pretty unworkable for most kind of settings. And that 1,500 gallons could be consumed rather quickly in a situation where that generator was running under full load for a continuous amount of time. So that was another example of an area where it sort of applying certain kinds of regulations and experience from other parts of governance, in this case above ground fuel storage, to a data center setting, which has a little bit different considerations. And let me just ask our panelists here. So how does if you're providing diesel fuel to these things, what does that look like? How is it stored for your generators that they access that fuel?
Typically, for most of the data center applications, the fuel is stored beneath the unit, whether you call that a belly tank or a day tank. They can take on several different terms. And then typically that's sized to operate the unit for somewhere between, I call it 8 hours. It's usually about a day worth of activity, whether that's 8 hours or 24 hours. Sometimes it's more. It could be dictated by code to be up to, I think it's 96 hours in some cases. But for most of these data center type applications, this is more around a day use of fuel on site, which for these large units that are consuming a lot of fuel, this could be several thousands of gallons of diesel fuel per unit.
Great, thank you for that. Okay, others want to weigh in on any of the policy considerations we've seen?
Alan, one overlap that we observed in the state was that the building codes for data center structures overlapped with prefabricated housing codes. And you could you could say that the data center enclosure is a prefabricated housing, but no one lives in it. When Mike mentioned the fan that operates on these, they're a wind tunnel. And so in operation, they're not occupied because it's extremely uncomfortable and unsafe. So that's one example. There could be other codes that are overlapping for good intent, but perhaps not for good reasons. So that's just something to keep an eye out for, is that those unintended consequences of existing rules that overlap and are misapplied. Again, safety always being a key #1 priority for these facilities and application of our products, but to not have overlap just for the sake of the rules written this way, applying that inappropriately.
Very good. Thank you, TJ. Go ahead, Mike.
One to bring up is, I call it emissions testing. We all want the units to be clean. We all want the same thing, and we want to know that they're clean. But what we're starting to see and get into the realm of is some local requirements or some emissions requirements for how often they need to be tested. We already talked about how low hours these units are already running, and there could easily be cases, and it needs to be thought about, of, do I run the unit to measure how much it's going to pollute, or do I just run the unit? Please understand, I'm not saying that we just run the units. They need to be clean, but we need to live in that juxtaposition of what is the right balance between that, to make sure that in some cases these units do run more for emissions compliance purposes, to verify that, than what it would if it never were to, and how much does it emit then, and how does that play into? These are good questions to wrestle with and to take into consideration.
The law of unintended consequences, and also mobile emissions testing, so on-site tailpipe, you can find that the measurement uncertainty and measurement error of just trying to measure the system can be outweighed, can actually be, the measurement uncertainty can be greater than the actual emissions coming out of the system. So then you get all of these compounding factors of, well, did you measure it right? And oh, now we need to drill another hole into the upstream pipe work to be able to put a different sensor in. And then when they take it out, it's not properly blocked, and these kind of things. So you can end up compounding a problem and creating a problem that didn't exist in the first place. So yes, you need to think about some of these things. We've got a lot of assuming you can tell, you should check that there's not been any tampering. You should check there's not been any kind of impact damage or any kind of other damage to the system. But if it's as designed, then it should work.
Thank you, Louise. We're going to go to our questions now here, but I think most of them seems to have been answered online. But there is a question here. I know Mike Sanford, you asked to answer live, and the question is about: is there a specific location, site, web link, etc., where we could go for the latest and updated applicable tier certification requirements based on engine capacity for emergency power? Any insights there?
I love this because the reality is that of course there's a resource. It's the CFR, the Code of Federal Regulations. The challenge with that is it's just quite honestly it's not terribly easy to navigate. Most manufacturers have published some sort of short form guide to help walk through the applicable requirements for high horsepower and small engines operating in generous applications, and work to simplify it. Compounding or maybe making that even more challenging is state requirements, or even more varied from county to county, city to city, or beyond. And so it can be quite challenging. My recommendation is always to work with the subject matter experts that live in this space every single day, because it's something that unfortunately we've come to grow with and to know, and can certainly share our insights in this space. I hope that addresses it. Unfortunately, it's terribly hard to provide a single source other than the CFR itself.
It's absolutely true. And we turn to experts like Mike and TJ and Brian, Louise, and Mary all the time for questions like this in this area because it is so complex. We have time for a couple more questions, and I see there are a few rolling in here. Considering demand response, bridge power, can we assume that Tier 4 will become the state of the art for DC in the near future? Mike, that had your name on it, I think.
Yeah, I think I put answer live, and I'm confident there's some
Okay.
others in the group here that may want to answer or to provide some insights as well. The challenge with blanket recommending that a US EPA stationary non-emergency or Tier 4 solution be used in every data center going forward is one part of it's the cost. You know, quite honestly, the cost of a Tier 4 certified solution is significantly greater than its Tier 2 counterpart. I'm not going to say it's an order of magnitude more, but in many cases, it can be twice or more the cost of that Tier 2 unit. It is not insignificant. Additionally, it does add a layer of complexity. And the one I'll point out most notably is for certified solutions. Certified solutions are susceptible to something called inducements. Inducements is the requirement mandated by the EPA that these solutions be self-monitoring, closed loop control, and take action to shut down the engine when it detects that one or more of its systems is not working properly. You may be familiar with this with on-road vehicles. It's commonly referred to as a like limp home mode is typically what it's called. And it's the idea that the engine will go into a low power operation in order to allow the user or operator to get to a safe location and then repair the system. The challenge is in the power generation space, an inducement causes a shutdown. And any Tier 4 system is susceptible to them. And for many operators, especially those outside of the data center space, like a hospital, for example, if that system were to not be functioning correctly and suffer a shutdown, that's quite literally lives on the line when that engine could otherwise operate. As such, that added layer of complexity and cost. And honestly, the lack of readily available solutions in the marketplace make it a challenging thing to recommend that stationary non-emergency certified Tier 4 be the go-to for all data center applications going forward. Now, Tier 4, what we commonly refer to as complying with Tier 4 emissions levels, achieving the emissions levels for both NOx or particulate matter is not uncommon. In fact, I would say for most data center applications, especially for oxides of nitrogen, that already is the standard, commonly referred to as best available control technology. And that really is the state of play for where we are today. I hope that's clear.
Very good. Thank you, Michael, and everyone. We're sort of at the end of the rope here in terms of time, so let me just go ahead and wrap up if we might. I think we've shared some information this afternoon about the role of these internal combustion engines in this space where it's rapidly growing both in data centers and we have lots of concerns about power. And this technology is one that's proven. It is the gold standard in many cases. And as you just heard, can achieve near zero emissions quite consistently. And it is an area where there's tremendous interest in policy. And we hope that today's session is the beginning of your educational journey to help understand these issues more. And we welcome the chance, along with our member companies, those represented here today, to continue to provide information and insight to those who are interested in learning more about this topic. So we appreciate everyone's time today. And let me see here. Oh, sorry, going the wrong direction. I do want to thank all of our panelists, TJ Tarabalski from Caterpillar, Mike Sanford from Cummins, Brian Ponstein from MTU from MTU Rolls-Royce Power Systems, Mary Derry from Innospec, and Louise Arnold from Johnson Matthey. We do have a series of resources available on our website. We have a new fact sheet out on data centers. It's only 2 pages long, so it only covers on the very top issues, but you might take a chance to take a look at that. And then we have another number of resources that have touched on this issue in recent times. So With that, again, thank you to all of our attendees and thank you to our panelists. We appreciate your time today. If you're interested in learning more about these kind of issues, we do have another session coming up, this time on propane, and we'll be looking at the role of propane in internal combustion engines later in October. So that's a separate registration, and you can visit our website to take advantage of that. But with all that, we appreciate, again, your time today. If you have any feedback you'd like to share with us, that's the way to do it there. And we'll have a follow-up email out to everyone about the link to the recorded version of this event shortly. But with that, thank you all, and have a wonderful afternoon.